So in this video, we're going to talk about Markov decision processes, which continue the story that we've been telling over the semester about how we can represent environments with state spaces or in some way that allow an AI agent to make reasonable and rational decisions on or in. So a Markov decision process essentially takes what we've been previously looking at and adds an extra twist, which is that it's a richer environment representation that allows for randomness. It allows for randomness that we couldn't handle before. So in the state space representation of a Markov decision process, we'll also have reward functions, and then we're going to talk about how to optimize what's called a policy, or you can think of it as a strategy to navigate the state space via an algorithm called value iteration. So this is the canonical example that we're going to basically be spending a lot of time thinking about, or at least something very similar to this. So this is grid world. So in grid world, we have a very simple board where we are the blue dot, or rather the agent we're going to be thinking about is the blue dot, and the agent is able to navigate through this grid. It can move up, down, left, or right. And it has there's a square that's colored in gray, which is one that the agent can't get through. That's a wall. That's an obstacle. And then there's two squares on the top right that have numbers in them. And these states have reward values. In fact, one of them has a negative reward value, which is a penalty. So the agent's goal is to collect this reward. So naturally you can sort of look at this board, and with our human intelligence we can think, well, you can just search for that one, or we can use our algorithms that we've studied so far to search for that one, to search for the path to get to that one. And that might look something like this, right? We take this simple path, and the way that we used to represent things in search algorithms, and maybe even in adversarial search algorithms, we've basically designed algorithms that return a sequence of actions, right? In this case, the actions would be right, right, up, and right. Okay, those are the directions of the arrows, and those are the actions you take that take you from the starting point where the blue dot is now to the best goal, the best reward, which is 1. Okay, so the difference in the Markov decision process representation is that actions don't always translate to state transitions. Like right now in the search algorithms view and the minimax view, or the adversarial search algorithms view, an action always leads to a state transition. It always leads to a particular transition to another node in our state space network, whether it's a tree or a graph. But in a Markov decision process, actions are actions and state transitions are state transitions, and they're not really as intrinsically tied as they've been previously. So what we have with these stochastic transitions is that we might try to move right. We might choose the action right, and something might go wrong. Right? Instead of our robot moving to the right, if this is a robot, its wheels might slip, or the terrain might give way, and it might stay in place. It might move up, but most of the time everything goes right, and everything goes fine, and our attempt to move right might succeed. Maybe that's a nice optimistic scenario, but not all the time. And so this might look like this, right? If we tried to execute the same sequence of actions of right, right, up, right, we might try to move right and fail. Okay, we failed, and now we didn't change state. Now we try right again, continuing the actions that we've already laid out by our search algorithm or by some other algorithm. And then we try to move up, and that's illegal because it hits a wall. We try to move up again, it hits a wall again, and then we move to the right. And that's where we land, because we memorized a sequence of actions. We were not robust to the fact that the environment might not allow us to make the actions that we want, or make the transitions that we want. We can take the actions, but the transitions might not happen the way we expect them to. Or worse, another example of this could be we successfully move right, then we successfully move up, and then for some reason our wheels slip. We try to move up and we slip. And then we move right with the final move and end up on the -1 square. So not only did we get no reward like we did in the first example, we actually got the worst reward. We got the got the penalty. Okay, so in order to handle this type of environment, or this twist on what environments can be, we're going to want to represent these things formally. So how do we do that? So we have a probability distribution over what state we end up in given the current state that we're in and the action that we choose. Okay, so think about it this way. If we're in a square and we choose the action up, we choose the action to move up, then there's some probability we're going to end up in the square above. There's some probability maybe we'll end up in the same square, and maybe there's some probability we end up to the right or left. But this function, this probability function, is something that is part of the environment description, right? It's part of the way we represent the environment. So an example of this is illustrated right here with these three states. So there's states A, B, and C, and let's say we're in state B, okay? And the action we choose is right. So normally this would be the whole story, right? If we choose right, or not normally, but at least in the things we've been studying so far, if we choose the right action, we're going to end up in C. That was the old way of thinking. Right now we're going to say, okay, well, if we choose right, A equals right, action equals move right, maybe we'll accidentally stay in the same place, or maybe we'll move to the left, like I said. And then here's where the values of these probabilities might come in. Maybe the probability we successfully move to the right is 0.7, and the probability that we slip and stay in the same place is 0.2, and the probability that we backslide maybe is 0.1. And so these sum to 1, so they form a valid probability distribution. You can think about just the fraction of time over all the trials that you're going to ever try this action from this state. What's the fraction of those trials that you end up in the subsequent states in C, B, or A? Okay. And the other thing to note is that this is a strict generalization of what we've seen previously, right? So you could imagine having a probability distribution like this, where it's a 1.0 that you end up in C, and 0 that you end up in the same state, and 0 that you end up at A. Okay, and that would be we'd call it a deterministic Markov decision process, which is pretty much what we've had previously, where we just had a function that returns the next state given an action. And here I've written out what these, how you map from these numbers I threw on the screen and these pictures I drew to the probability function, right? So the probability all the way on the right, the probability of state C, given that you're starting in B and you take the action right, is 0.7, and then the probability of that you're in B, given that you're in state B and that you take the action right, is 0.2, and the probability that you end up in A, given that you were started in B and took the action right, is 0.1. So now suppose we move to the left, and suppose when we try to move to the left, we get these probability distributions, or this probability distribution. Okay, and maybe this basically implies that moving left is slightly more successful than moving right. Maybe this could be something in the terrain again, or it could be something about the nature of transitioning from states. But the idea is that we've written out completely different numbers, completely different probability distribution for a different action, right? So you plug in whatever action that is available for you from state B, and then you get the probability distribution back. Or when we design these processes, we have to consider all the actions from every state. Okay, and as an aside, you might have heard about Markov models, maybe in other classes. Maybe if you took econ or some probability or some stats classes teach these things, or maybe if you're learning machine learning, you might have learned about these. So there are these things called Markov models, which are kind of a simpler version of the Markov decision process. Basically, a Markov process is where you don't have the actions, right? So you don't have a decision to make. So that's a easy explanation for why the things are named the way they are, right? Markov decision process versus Markov process. So in a Markov process, you don't have a decision to make. All you have is a bunch of states and a bunch of probabilities of transitioning between states. And people use these things to model transitions between modes of like the economy, right? So here's an example. Try not to show this to any economics professors. They'll be really mad that I'm really misrepresenting what actually happens in real economies. But here's one maybe plausible model for how things behave in economies. So maybe you have economic bubbles, and if you're in a bubble, you have a 0.9 probability of staying in that bubble. But then every now and then, in 0.05 of the time, you move from the bubble to a stable economy, and 0.05 of the time, you move from the economic bubble to a burst, and you get a recession. And then maybe a recession stays a recession 0.75 of the time, and sometimes it transitions to the stable economy, et cetera, et cetera. Let's not think too much about this. But the important thing to note is that in a Markov process, there are no actions. Right? So it's just the transitions. It's like thinking of a Markov decision process where there's only one decision. There's only one option in every state, which is just to move on to the next time step. So a Markov decision process gives us a little bit more agency, which is very fitting, right? So it allows us to task our AI algorithms with a decision to make at each time step, at each state that you're in. Okay, so getting back to Markov decision processes, let's think about the reward function. So we saw this very simple grid world with a reward function of a 1 and a reward function of a -1, which is a penalty. So this is the slippery bridge variant of grid world. And the idea is that you're at the blue dot, and you can see that there's a reward square on the left. You can get one reward, a reward of 1, if you move to the left. But if you move to the right, all the way across the bridge, all the way to the right, there's a 10, right? And then along the way, adjacent to this path of 0 reward, there are these -100 squares. These are the penalty squares. And what this is meant to represent is a situation where a robot is on a bridge. The bridge is all the empty squares with 0 reward. And across the bridge, there's a pot of gold. That's a 10. So you're really going for that. Or if you really want to get the highest reward, you go for that 10. But the problem is the bridge is slippery. So when you try to move right on the bridge, maybe you'll slip off the bridge and fall down into a chasm, and that's worth 100 or -100, right? So you get penalized hugely if you fall off. And so the question is, this is I guess a representation of many problems we have of risk reward in real life, is do we risk crossing the bridge to get the 10 reward, or do we just take the 1 reward, take the safe way? So the way we answer questions like that, of what do we do in this environment, of how do we get a good reward in this environment, is we propose a policy. So we try to come up with a policy, which is a function, or formally you can think of it as a function of the states that just tells you what action to take in any state. Okay, and this is richer. This is much richer than a sequence of actions. Right? Whereas before we saw that example where if we just write down a sequence of actions, if your transition takes you someplace you didn't expect to be, you don't know what to do anymore if you just have a sequence of actions. But now if you have a policy, then the policy, you can always evaluate it into this in this new state that you accidentally found yourself in, and it will tell you what to do next, what your action you should try to take. And so here's an example of one possible policy that you could that you could consider in this slippery bridge world, right? So you can see that I did this by hand, so you might see how I'm thinking about this. It's basically a very greedy policy. The greedy policy tries as hard as it can to get to that 10. And even if it's in the 1 spot, even if it's in that safe reward spot all the way on the left, it's going to still keep moving right and try to get to the 10. And then if it falls into the chasm, if it falls off the bridge, it tries to get back on the bridge. So here's a question: is this a good strategy? Is this how do you know if it's a good strategy? The answer to that is that you don't know. We don't know if it's a good strategy because we don't know the transition probabilities. In this graphical representation where all I've shown you is a grid of states, there's nothing on the page right now on the screen that really tells you what the transition probabilities are. For example, you could imagine a situation where this strategy might be, or this policy might be a better one, right? So in this policy, if you're on the bridge but you haven't gone far enough, maybe you want to move left and stay and get that one reward and be safe instead of risking crossing the entire bridge. I don't know. It depends on the transition probabilities. So even if we have these transition probabilities, then we want to ask ourselves, how do we measure how good a policy is? So here's one way to do it. We're going to use the function u to represent the utility of a sequence of states. Okay, I mean, this is pretty kind of an obvious way to do it. So what we're going to do is we're going to say the utility of a sequence of states is the sum of all their reward values. And in this grid world thing, many of the states have zero reward, and when it's zero reward, these diagrams usually don't write the reward value on the screen, just to eliminate clutter. But most of the time that's zero reward, but that's okay. The point is that for every state in the sequence, you have some reward value, and you're just going to sum them up, and that's fine. That's a reasonable way to start. One of the problems is that what I've written here is that the sequence of states that you reach goes to from 0 to t. So there's t states in this sequence. In many settings, we want to consider agents that operate indefinitely, right? So they operate forever. They say they just run around in the environment and try to collect rewards, and they are they're just rewarded for living in the good states and avoiding the bad states. So if we want to have a function that evaluates the quality of a sequence of in infinite states, because time in this scenario would go on forever, and the agent would live in the environment forever, that value is going to be very easy to end up being infinite, and then it's very hard to make a decision about what's a better policy. So one strategy for handling this, which is the strategy we're going to pretty much use throughout the rest of the segment of the course, is to use a discounted reward. Okay, and what this is a you put a number in front of you multiply each reward by some number that's a sequence according to the how far in the future we're talking. So state 0, S0 is the current state, S1 is the next state, S2 is the state after that. So ST is t steps in the future. And in some sense, what this does is it makes you a little bit greedy about making a decision that helps you immediately versus planning ahead and trying to make a decision that's going to be farther down the road, or that's going to reward you farther down the road. So this gamma parameter essentially shrinks the amount of influence you get, or amount of reward you're going to consider in the future. So if this is 0, then all you care about is the next state reward. But if this is 1, then you care about all the reward forever. But if it's something in between the two numbers, then you get that you will slowly decay how much you care about future rewards. Okay, so far what we've seen is just a function that takes in a sequence of states and tells you how much reward you get. And that's not super helpful right now, or at least it hasn't gotten us very far, because what we want to evaluate, what we want to think about a policy, and given a policy, how good is it? And what all we have now is just a defined way of thinking about a sequence of states and the reward you get for that sequence. So let's take this a little bit further. So first thing I want to do is just I've already hinted at this, but let's just say this sequence goes on forever. So it goes on to infinity. So instead of to capital T, it goes to infinity, and the sequence is infinitely long. Or equivalently, t equals infinity. Capital T is equal to infinity. So now what we're going to do is we're going to write a more general utility function for states and policies. So this is u with a superscript of pi of s. So if you're starting from state s, what this says in English, just forget about the math for now. In English, it says if you start from state s, what is the expected utility of all the sequences you could see from starting from state S. Okay, and that's what that little probability in the subscript is. And what this, what the math says is the expected value over the probability of all state sequences of that state sequence score that's upstairs. Okay, and given that, right now this is a function. Now this is a function of a policy and of a start state. And so then if we know what the initial state is, what S is, then we can just say, okay, here's the function we want to maximize. Here's how we decide what is the best policy for us. And the best policy for us, starting from state S, is the policy that gives us the highest expected reward for over the probability distribution of all sequences that we can get starting from state S. So that's fine. That sounds fine. But what's weird about this is that we actually now have a definition of a optimal policy for every single possible initial state. And that's kind of weird. But the good news is that things actually simplify a bit. And the textbook gives a really nice intuition as to why this simplification works. And the idea is that, it's written down here within math. If you work through the equations, it says that this is the expected, or this is the score starting from state S. And the score is for a policy that will tell you what to do in any state. It will tell you what to do, no matter what state you end up in, right? And the point is that if you imagine a different policy, a policy starting from a different state, that also has to have actions. It has to suggest actions for every state on the board, every state in the environment. So for what reason would, just purely intuitively, forgetting about the math, imagine just one policy. If you reach another state, let's call it A, you reach state A, that policy tells you to take another action. Let's say it tells you to move up from A. And this is the optimal policy, right? This is the optimal policy starting from state S. So if the optimal policy starting from state S tells you to take action up from state A, then there's some other policy. There's some other optimal policy starting from S prime. There's a different optimal policy, and it also considers what to do when you're in state A. Why would it be a different action? Why would it not be up? It would have to be up because that was the optimal move, right? If an agent using the original optimal policy ends up in state A, it has to move up, and that's the optimal move for it. It doesn't matter where it came from previously. It just matters, what its future reward is going to be. So that's really good news. That basically means that this initial start state that is part of our definition of the sequence score, of the utilities of sequences, that ends up being as part of the definition of the expected sequence score, and ended up just by derivation as part of the definition of the optimal policy, it basically can go away because we can say, it's the same policy. This policy is the optimal policy for state S, which also means this is the optimal policy for any other state S prime. So we can just drop the S subscript. So then as a result, we can also drop some other notation to make things a little bit cleaner. We can just say, the utility for, the optimal policy S we're just going to call it the utility of S, right? We're just going to say that the utility is implicitly defined to be the utility, assuming you're going to use the optimal policy from there on. Okay, and then the policy can sort of be recursively defined by using this utility as saying that, when we take when we are at state S, we're going to look at all the probabilities of the different transitions we can make given an action, or more succinctly put, we're going to compute the expected utility, where the utility has been defined by this sort of optimality, this optimal strategy utility. We're going to take the expected utility of the states that we'll end up in if we take an action A, and then we choose the best A. So this should all kind of start to look familiar. It was a little bit kind of a windy derivation, But the summary is that U of S, this utility score that we're focusing a lot of attention on, U of S, or S prime in this case, is the expected utility given optimal play from S prime. Right? Doesn't that sound familiar? It should. And the idea is, we don't necessarily know what optimal play is from S prime is, right? If we want to compute this policy, we start out with the idea that, yeah, we know that we want to play optimally. We want to think about what happens if we play optimally, but we don't know how to play optimally. If we did, we'd be done. We wouldn't need to compute anything. So, another way of writing this down is that the utility is the reward of the state plus the discount factor times the maximum expected utility moving forward. And this is a famous equation. This is called the Bellman equation. And you probably have heard Bellman's name all over computer science education. He's one of the co-inventors of the Bellman-Ford algorithm, and he's done a lot of things. But this is one of his famous named equations, and it basically says that this whole thing is very recursive, just like we've kind of seen before. It's that the utility is the reward plus the future rewards, and the utility is also all the future rewards. I mean, it's kind of weird. So, okay, the utility is the expected future rewards for an infinite sequence, and that's defined with this recursion because you can use the fact that if the utility is actually the expected future rewards, you can just use that for your neighboring states, for the states that you can transition to compute it via this Bellman equation. Okay, now how do we compute this? How do we use this to now find an optimal policy? And the trick is that we're not going to try to directly find an optimal policy. We're going to try to find these utility scores, and then that will tell us the policy. Right? The policy we already saw on the last slide, or even at the top here, it's pretty clear. The policy just looks at these utility scores. So the trick is now we need to compute these utility scores. Okay, and it's pretty weird because the algorithm to do this the simplest algorithm to do this is something called value iteration, and it looks like this, which should look pretty familiar because it looks almost exactly like what we just saw. This is the Bellman equation on the bottom. The update on the top is the value iteration update. And if you look at it and you see what I'm talking about, why they look the same, they're exactly the same, right? They are exactly the same thing. The only difference is that the value iteration version, it has the left arrow notation to indicate that it's an assignment, so it's an algorithm. You're assigning the next version of your utility score to be the definition of what would be the utility score if U of I, the current utility estimate, was real. And you can stare at this and think about, why would this work? I mean, why would this work? Basically, what it's saying is, assume that your utilities are correct. Now compute the utilities. And for some reason, if you keep repeating this, your utilities in the end up actually being correct. And that's a little bit weird. There's some math in the textbook that you can go through if you're interested in seeing the analysis of why this converges to an actual solution. But it's actually useful maybe to think about what happens with this update equation when it runs an update and nothing happens. In other words, when it converges, when it's done. So what would it mean for us to run an update, upstairs, the equation on top? If we run that update and nothing happens, right? U sub I plus 1 is exactly equal to U of I, U sub I, right? So if that didn't change at all, what that basically means is exactly the Bellman equation. It means the Bellman equation is true, is satisfied, is correct. Okay, and if that's really good news, because that means that when we converge, assuming we converge, and I defer the analysis of whether we actually do converge, but when we converge, we will have satisfied the Bellman equality. Okay, so let's run through an example of this. It's a little bit weird, but it sort of makes sense. I mean, another thing you can think about is like I said, we've seen something like this before. That recursive max inside this update equation is very similar to minimax basically, right? Or maximax or expectimax. It's kind of the idea that let's assume, we basically assume that we're going to do optimal later on, and now we compute, for our own decision. Let's worry about our own problems, and our own problem is to maximize, assuming that the u sub I is telling us the truth. We need to make the best decision for our current decision, and then that iterates somehow, and we end up at the solution where it really is the true optimum. So let's run through an example. So here's a very, very simple Markov decision process. There's two states, a left one and a right one, and the left state has a reward value of 3, so that clearly is the state we really like. The right state has a reward value of -1, okay? And the two actions that are available are red and green. So the red action is, I guess the analogy I was going for is that the red action is you try to stay in place. Okay, so the red action is you try to stay in place. You try to stop, right? Just like in a traffic light. And a green action is you try to move. You try to switch. You try to switch which state you're in. And in fact, if you look at the green arrows, the green action always succeeds, right? It has a 1.0 probability of switching which state you're in. And then the red action, it succeeds when you're in the bad state. It succeeds in the right. So if you're in the right, you can always stop and stay in the right and take more penalty if you really want to. But if you're in the left, if you try to stop, there's a 50% probability you'll end up back in the bad state. Okay, so this is clearly a very toy problem, but you can just imagine that this could represent something like, I don't know if this actually works, but imagine you're trying to run a race and there's two modes you can be in. You can either be in, you can be sprinting or you can be jogging. And maybe if you try to stay jogging, you can always do that. But if you try to sprint, you can always start sprinting, but if you try to stay sprinting, you get tired and you can start jogging. I don't know, it's not the best analogy, but it's just a toy example with two states. It's an easy one to draw on the screen. It turns out that Markov decision processes are kind of hard to draw because you have to consider all the different actions. So I've color-coded here, but if I made this any more complicated, it would be pretty hard to read. But let's start trying to compute those utility values, right? So let's throw the update equation up on the screen. Let's, just for the sake of this example, we'll say gamma is 0.5. So the farther we go into the future, it's going to decay pretty fast. So that means that we sort of care about the next reward we get in the future about half as much as we care about the current reward. Okay, and we start with utility scores of 0.0 as sort of just an arbitrary initialization. It turns out that it doesn't really matter that much how you initialize, as long as it's not really, really gigantic or completely wrong. You sort of want it to be on the same scale as the reward values, which are 3 and -1. Okay, but let's make some room. So let's start running these updates. So let's do the update for the left state first. So what is the utility for the left state? So we're going to plug in the numbers, and we get this. So we have, R of S, or R of left, is 3, and you add 0.5, which is gamma, times the max of, probability 1 of getting to the right state, but that utility is 0.0, and then probability 0.5 of staying, that's 0.0, times plus probability 0.5 times 0.0. So all the utilities inside that max function are just 0 right now, so we get 3. The answer is 3. Okay, and then moving to the right state, we have pretty much the same thing, right? So we have the reward of -1, and then we have gamma times basically 0 because our initial utilities are 0. So that was easy. So now our utilities are 3 and -1. Okay, that's our current best estimate of the utilities. So let's continue updating. So on the left, we have 3. Again, the reward value just keeps popping in each update. Plus 0.5, which is gamma, times now it's the max of one action, the green action, which is takes us with 1.0 probability to a state that we are currently estimating is worth -1. Okay, that means that the first option we have is to get -1 utility. Okay, now the second option, we get 0.5 probability that we stay, and we get 3 total reward there. And then 0.5 of probability we move to the right and get -1. So if you do the math out, you get that we have a choice of getting -1 reward, -1 expected reward, or 1.0 expected reward. So we want to take the max, so we get that the total estimated utility becomes 3.5. And on the right, we can do this again. We get -1. That's again the basic reward, the reward that's given to us by the environment, plus gamma times the max of 1.0, the 1.0 probability of moving to a state that has a utility of estimated utility of 3, and then a 1.0 probability of us, if we stay, of us getting -1. And of course we won't pick the -1 because we're trying to maximize, so we end up with a 0.5 score. So we can run this a couple times more. If you want, you can probably pause the video or something and check the math, but it's basic arithmetic at this point. And you can see the numbers sort of converge a bit. So actually, let me back up. So it would be useful to see this from the beginning. So if you see starting from the beginning, let's just watch the numbers now. So forget about the equations. Forget about the equations that are going to pop on the screen. I'm going to just cycle through these slides. So you see we get 3 and -1, and then now we get 3.5 and 0.5, and we get 4.0 and 0.75, and then we get 4.2 and 1.0, then we get 4.3 and 1.1, and 4.4 and 1.2. And I didn't do all these by hand. I actually computed some of these with some code, just because even though this is a tiny example, I got pretty bored doing these by hand. But here's the interesting part. This is where it converges. It actually converges to these. The previous slides I was rounding. This is not rounded. This is the actual numbers. So it's 4.40000 and 1.20000. Okay, so this is the actual converged utility value for this example I drew up on the screen. So that's great, I guess. I mean, it's not really that exciting because these are just random numbers or not arbitrary numbers. But one question that's kind of interesting to ask is, did this really work? Did this really converge? Well, let's think about it. So how can we check that? We can check that by plugging these numbers into the Bellman equation. And so let's do that. So when we plug in the numbers, we have that, the number we're going to be looking for is, 3, the reward, plus gamma, which is 0.5, times the max of 1.0 transition probability to get to the state that we have estimated to have a utility of 1.2, right? So that's 1.0 times 1.2. Then 0.5 probability of us staying in the 4.4 utility state, and 0.5 probability that we end up in the 1.2, okay? And if we do the arithmetic, we just get that, that's either 1.2 or 2.2 plus 0.6. Okay, and then finally you do the math out fully. You're going to pick the 2.8, not the 1.2, and so you end up with 4.4. Okay, that's good, right? Because 4.4 is the value we want. So this means that recursive definition is actually true. Is actually finally true for these values of u, right? These values of the utility function. Okay, so that's pretty much it. So to summarize, we talked about Markov decision processes, and this is again, so it's important to separate the state representation or the environment representation from the algorithm for doing AI in the environment. So a Markov decision process is not. It sounds like it's a smart AI representation or something. All it is an environment. It's a dumb environment. It doesn't do anything smart. It doesn't do anything rational. It's just a place that we can stick our AI agent, and the AI agent can try to do something smart in. But it is just an environment. It's the maze for the rat. Okay, so the Markov decision process is the maze where the actions now have probabilistic state transitions. That means that the agent, the rat in the maze, gets to choose an action, and when it chooses an action, the maze determines where the agent ends up, where the rat ends up after choosing to move one direction. Okay, the rat analogy is not working as well anymore, but the point is that the agent chooses the action, but the Markov decision process takes that action as input and determines what state the agent ends up in. Okay, and to start to think about making rational decisions in Markov decision processes, we came up with a definition of a discounted reward function that enables us to think about future rewards even in infinite time series. Right? Even if we say this agent's going to wander around the state space until infinity, until eternity, we can still think about that with finite numbers. So the discount reward function just sort of weights the future rewards less. And we talked about the notion of what an optimal policy does. An optimal policy is going to maximize the expected reward or the expected discounted reward. And and wrapped up into this, we talked about the definition of a policy, which is just a function that takes a state and tells you what action to do. And finally, we got to an algorithm that can compute an optimal policy called value iteration. Okay, and this is it basically just computes the values, assuming it knows the values of every state. It updates values based on its assumed values, and eventually that converges to the point where the updated values and the assumed values are the same number, and that you can show with some math and some thinking, or maybe just if you want to trust me, that is actually the optimal value. Okay, and the material for this stuff is in the textbook in chapter 17, and it goes until the end of chapter 17.2 or section 17.2, and we'll get onto the later stuff later, so you can read ahead if you want. We're going to go through pretty much everything in chapter 17 eventually. But just be careful. Some of the book, because we're going out of order in the book, it references some of the previous chapters. So you might want to flip back when it does reference something, but you don't have to. Most of the concepts are pretty easy to get without the knowledge that they're referencing in the referring to the chapters we've skipped so far. And some of them we're actually going to go back and read completely out of order. So you'll be fine there. All right. And lastly, I wanted to leave you with this thought. I mentioned in the class the other day that the transition between what we've been studying so far with the game trees, these adversarial game trees, and Markov decision processes is the expect to max problem, right? So where we have a game tree where we have one type of agent, a max agent, that's trying to maximize its score, and when it makes a move, the next turn is the chance node's turn. Is some random process that takes some rolls a die or something and determines what state you end up in next. So that's very, 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 very similar to a Markov decision process, and in many ways it's almost exactly the same thing, but it's not exactly. There are some very subtle differences. So let's think about and talk about in class what are the differences between an expect to max representation and a Markov decision process. Okay, see you in class.